Chapter 17, Radioactivity. First, let's look at the composition of an atom. It's made up of protons, neutrons in the nucleus, and the electrons orbit around the nucleus. The electron has a -1 charge, proton +1, neutron is neutral, 0. Standard names and notations. This capital X here is the chemical symbol, which is obtained from the periodic table. A here is the mass number or the nucleon number. Z here is the proton number, the number of protons, or the atomic number. So if the element has the same number of protons but different number of neutrons, they are called isotopes. So one example of isotope here is the helium isotope. This has 2 protons, 1 neutrons. Here has 2 protons, 2 neutrons, and they are the isotope of helium. One quick question: which two are isotopes? So isotopes have the same number of protons but different number of neutrons. So the answer is P and Q. Okay, what is radioactive decay? It's the random process by which an unstable nucleus loses energy by emitting alpha particles, beta particles, or EM radiation in the form of gamma rays. This process is spontaneous, means it's not triggered by external influences, and it's random because you cannot predict the direction of radiation or when it will occur. So these are the 3 types of nuclear emission. Let's look at alpha particles. The ionizing effect is the highest for alpha particles, followed by beta and then gamma. The ability to penetrate is the least for alpha particles. It's stopped by merely a piece of paper. For beta particles, it's medium. It's being stopped by a few mm of aluminium. But for gamma radiation, they can penetrate deep into materials, which means they can only be stopped by very thick concrete or lead. Okay, looking at alpha radiation. So alpha radiation is when the nucleus emits 2 protons and 2 neutrons, which is 4, 2 helium. So you can see alpha particle as a helium. So this is the element radium, which decays into radion and helium. Beta radiation. So for beta radiation, the neutron in the nucleus transforms into a proton and an electron. Okay, so this example here is when carbon-14 becomes nitrogen by emitting a beta particle. So a beta particle you can see as an electron. For gamma radiation, the energetic nucleus actually loses energy by emitting high-frequency EM wave. And this high-frequency EM wave is gamma ray. Okay, let's look at this example. A nucleus of magnesium decays into sodium by emitting a beta particle, which is an electron, and the equation is shown as this. So the mass number does not change, so P still remains 23, but this time Q here will gain 1 proton, so it becomes 13. And the answer is D. So what is background radiation? Radioactive materials actually do exist in nature. They can be found in food, soil, or in plants. However, most of this radiation is small and not dangerous. Okay, let's look at half-life. So half-life is defined as the time taken for radioactive nuclei in a sample to decay. This radiation is actually being detected and measured by this Gardner-Muller counter. Okay, so it can be counted in terms of counts per second or counts per minute. So fewer radioactivity means lower number of radioactive nuclei. So here we have this number of iodine 131 atoms, or we can actually have it in the form of activity per becquerel. So this symbol is actually for 1 BQ is equals to 1 decay per second. So it's a measurement of radioactivity. So to find half-life, we can start with 120. You see that it becomes 60 here in 8 days. From 60 to 30, another 8 days. 30 to 15, another 8 days. So we can see that this is the half-life. Okay, let's look at one quick example. A radioactive source has a half-life of 0.5 hours. It has an initial reading of 6,000 counts. What was the reading after 1.5 hours? So one half-life is 0.5 hours. 1.5 half-life is 3 half-lives. So 6,000 will become 3,000. That's 1. Becomes 1,500. And it becomes 750. So answer A. Okay, so let's look at the uses and hazards of radioactivity. So if you have a fracture, we can actually use X-ray to actually check for the fracture. However, you must remember that these are actually given in low dose and short half-life. Okay, then it also can be used to destroy cancer cells. Okay, so it's a form called radiotherapy. It's done in National Cancer Center under NUH. Okay, it also can be used to measure thickness of materials, which should have been done for the submersible. It also can be used for carbon dating to check the age of fossils. So what are the hazards of radioactivity? We said that with controlled amount we can kill cancer cells. However, it does do damage to healthy cells that are nearby the cancer cell. And leakage of radioactive substance can cause illness and death to living things. That's why the cleaning of nuclear waste from nuclear plants are actually buried deep under the ground, and it's actually expensive and costly to deal with. And that's all for this chapter.